possibility. It can actually radiate energy. So systems can gain energy when they get hotter. They actually radiate energy. Or release energy. I don't want to say release, yeah, I guess I can say release.
Releasing that same energy or some of it, or?
Not necessarily the same. Perfect example. You take your stove top, you turn it on to high, and you put your hand over it. You can feel the energy as it starts to warm up, come off of it. And if you lick your finger and touch it, I say lick your fingers, you probably don't want to just touch it directly. If you touch the burner, its temperature is hotter than it was before. Which means whatever energy is being released, that's not all it's absorbed, because it's hotter than it was before. It's at a higher temperature. Does that make sense?
Radiating some of it.
You radiate some of it. Now there are conditions where you can radiate all of it. Fluorescent lamps are a good example. They don't get all that hot, but they radiate a whole lot of energy when they start getting inside it. So that is a possibility as well. But usually they just radiate arbitrarily. They can radiate energy. Other things that can happen is that you typically get changes in intrinsic physical properties. Things like density, resistivity, which we haven't talked about, elasticity. There's all kinds of physical properties. And those physical properties these might be things like change of pressure, change of density, change of, we use the same letters, so electrical resistance. So if you think about an electrical circuit, the reason they have these big air conditioning units and fans in the back of your computer, you don't want it to get too hot. Why? Because when they get too hot, the resistances and the tall of the individual, not just resistances, but the other properties, dielectric properties of all the circuit components and all these little boards, they start to change. And when they start to change, the currents that they're expected to work under, electricity change. And when they change, you can fry boards. Even if you don't fry boards, long before you get to that, you just get malfunctions because they don't work properly. You're looking for a 5-volt signal to switch a transistor on, but you're getting 7 or you're getting 3. And either doesn't turn on or it turns on too early, or any number of other things can happen. Okay. So, if it's an intrinsic property, and in many cases a extrinsic physical property, they will typically change. And another one, by the way, which we'll have to deal with at some point here, volume.
That's kind of wrapped up in density.
Yeah, it is. And so, in other words, think of it this way. How do you know when something has gained energy? Thermally. It's got a different temperature than it had before. So electrical or density properties change, right? Or maybe it glows, or it was glowing and it cools down. Right? So those are observational, those are empirical, those are experimental, if you will, but they have physical consequences. There's one other one here that's not obvious, and it happens in spite of these two, especially. Celsius, it doesn't just keep going up as you turn the burner up higher and higher and higher.
Evaporates.
It's
Water
got-
evaporates, it changes phase. So the other
the
possibility
liquid
is
can't take up that much volume.
the energy that comes in physically changes state. Or contributes to changing the state of the Celsius. And yeah, I guess it's loosely related to volume, but it's much more profound. So let's just add that one here because big one. So it's pretty easy to observe. And typically then, here's what we have before we go any farther. Any of these things happen, we say it's gained internal energy, or another way of saying it. There is heat transfer to or from the system. And typically we use the letter Q to indicate heat. Big Q as opposed to little q. So there's either a heat gain or a heat loss. So I want to take this perspective. So one of the first obvious ones is basis of the original thermometer. Things get hot, they expand. If things cool down, they tend to contract. We'll leave gases out of here, but certainly liquids and solids. There's one caveat to this, or one exception to this, which is water. Water is most dense or most contracted at 4 Celsius, 277 Kelvin. The reason is when water starts to form ice crystals, the ice crystals take up more space than liquid water because of the complex shape of the water molecule. So, from just about everything else, if it absorbs energy, heat energy, it expands. Relationship, and we either refer to that in a linear sense, in a one-dimensional sense, we call it an expansion. The corresponding volumetric change, volumetric or volume thermal expansion. Okay. And I always think about this, sometimes I call it the George Costanza effect. There's an old phrase that a Dutch friend of mine told me one day, one summer day when we were having a conversation on his farm, and his cat was all spread out on the concrete in the shade. And you can tell the temperature of the cat, or the temperature by the length of the cat, because they like to spread out and stretch out so they can cool down, get that surface area spread out. So I always thought that was kind of a cute expression. Now, here's what's relevant to this. In linear thermal expansion, the relative change in physical dimension, I say relative change, is directly proportional to temperature change. So for linear thermal expansion, the best way to think about it, not the way the textbook explains it, is to look at a system, say a piece of metal, and initially at some temperature it has a certain length. But as it gains temperature, it's going to expand, or it would even cool down or it would shrink if it cooled down. But either way, the relationship between temperature change and relative shrinkage or enlargement directly proportional to temperature. And then there's a physical process. Well, I always think about that famous Seinfeld episode where George Costanza jumps into the Hudson River in the winter, And he's changing clothes later on and in the bathroom, and one of the co-stars, Elaine, opens the door.
Shrinkage, it's the shrinkage.
Shrinkage, yes. And I remember his statement, "The water was cold, damn it!" So as she started laughing and walked out of the room. So, nonetheless, then, what we basically have is, and by the way, here's another one. Coefficient of thermal expansion. It's a physical property. So what do you think happens to this property as temperatures change? It changes as well. It doesn't change as drastically as this stuff. All physical properties themselves are intrinsically temperature dependent. So always have to be a little bit careful. But the idea.
We're not talking about a constant proportionality anymore. This is just something.
Yes.
Is it like a bulk modulus kind of?
Yes.
Okay.
Bulk modulus is another example.
Okay.
Only bulk modulus represents a elasticity property. In other words, you push on something or pull against it, and it measures the resistance to change in size relative to force applied. This is purely an internal thermal effect or a temperature effect. So it's very much analogous, but it's subtly different in that it's related to thermal or temperature properties and not just force compression. I'm glad you brought that up because it's very closely related. So this is the basic idea, and it's relative, if you will, size change. So any system where you're concerned with length, for instance, maybe using a number of concrete pillars to support a building or to support a floor. And you got pillars up above. Temperature changes will affect compression or will affect thermal expansion. Well, that's fine if they're all the same, but if you got some wood and you got some concrete, they may not expand at the same rate, which could result in warping of the flooring, which could result in buckling or cracking or just pure structural failure. Sidewalks, we put little gaps in the squares. Roadways, bridges, certainly, we put little gaps between the segments of pavement. You want to make sure that the supporting structure, everything, when it heats or cools down, you don't get buckling, potentially have structural failure. Bridge going down, bad. So, this is the basic model, and it's based on temperature, and the implication is we're not looking at large enough temperature changes where this value changes much. It's relatively constant. Okay. Now, similar to this, if you look at a system broadly, not only does a system necessarily change in one dimension, but if something warms up, it will change in as many as 3 dimensions. And if it does, its volume changes. And its volume will change based on how its dimension this way changes and this way changes, not just this way. So you have concomitant expansions in all 3 axes. That's an important point, even though usually there's one critical axis. It's a structural concern, certainly. But relative change in volume follows the same model as relative change of just linear length. And for most substances, you add an alpha, or you add a linear coefficient of thermal expansion, linear, for all 3 directions. So it ends up being 3 alpha. Now the textbook, I think, may call this beta, but it's a 3 alpha property. So it's easier to think of that because 3 alpha is called the volume. Thermal, excuse me, volume expansion. Coefficient. Basically, somebody just measured length or volumes and said, okay, I'll warm this up, how much does it change? Warm it up some more, how much does it change? Warm it up some more, how much does it change? Get a straight line and get the average proportionality that relates temperature change to relative volume change. Sometimes we write this, and I think the textbook also calls it beta. And the reason it does so is that every once in a while, you get a substance that doesn't expand equally in a relative sense in 3 dimensions. An example is highly organized pyrolytic graphite. HOPG, highly organized pyrolytic graphite, consists of tubes, if you will, rings of carbon laid on top of each other. In sheets. So it's not symmetric the way the atoms are laid out. So it will expand differently this way than it does in the 2x, y dimensions. So some substances will do that. When that happens, this does not equal. But we're not going to deal with that case. But I only point that out because at some point in an engineering structures or thermodynamic class or strengths of materials, you're going to see it. But the simplest way of thinking about it is when you have normal, isotropic, uniform substances equal in all dimensions. Okay, so there's some other information that are mathematically relevant, but I'm not going to belabor it. Let's take a break now, and we'll come back and maybe extend this idea a little further or even go to broader implications. If you have any questions, please ask. I'm not trying to rumble through this stuff, but I'm trying to lay it out so we can focus on how you use it and get applications. But it's subtle, but it's extremely